Convergent boundaries are places where two crustal plates are pushing together. There are a couple of different kinds of convergent boundaries, but the most important one is called a subduction zone. We've already seen that new ocean crust is forming all of the time at mid-ocean ridges. This process has to be balanced out by losing crust somewhere else, and that's what happens at subduction zones. Subduction happens when the ocean crust cools enough that it becomes as dense as or denser than the underlying mantle rocks. This causes the ocean crust to start to slide back into the mantle. In the diagram at the top, a section of ocean crust and continental crust are sliding towards one another. The ocean crust dips down under the continent and into the mantle. Whenever a section of ocean crust moves towards continental crust, it's the ocean crust that is subducted because it's denser than the continental rocks. The lower diagram shows the same pattern in a collision between two sections of ocean crust. This process of subduction results in the recycling of ocean crust. As the subducted crust returns to the mantle, the heat of Earth's interior melts the downward moving plate so that it merges with the rest of the mantle. This also explains why we don't find any old ocean crust. It simply doesn't last more than a couple of 100 million years before it's recycled. Subduction is the most important feature of plate tectonics. The downward pull of ocean crustal plates is a key way that the plate motions can be tied to the convection in the mantle. In effect, the weight of the plate sliding into the mantle helps pull the rest of the ocean plate across the surface. In fact, when the first detailed radar maps of Venus were made in the early 1990s, scientists were looking for signs of subduction. When they didn't find it, it proved the most convincing argument that plate tectonics is not occurring on Venus.
There are several key things we can see at any subduction zone. The first obvious feature is long, narrow trenches, marking the location where the ocean plate is being forced under the plate it's moving towards. For example, in this map of the western Pacific Ocean, you can see the Marianas Trench, which marks the boundary between two sections of ocean crust, the Pacific and Philippine sea plates. The Pacific plate is subducting under the Philippine plate here, creating the deepest point in the Earth's oceans, Challenger Deep. Notice that there are other trenches shown as dark blue regions elsewhere in this part of the Pacific. The next obvious feature is chains of islands or mountain ranges. These form on the edge of the plate that isn't being subducted. A fine example of this is the Andes Mountains of South America. This long chain of mountains extends along the entire west coast of the continent. In this map, you can also see the deep trench just offshore from the Andes as well. Here, the South American plate is pushing over the Nazca plate. Another feature we see in subduction zones is plenty of active volcanoes. Water and low-temperature rocks like carbonates release gases at the high temperatures of the upper mantle. These gases work their way back up to the surface and help power volcanic activity along the plate boundary. Mount Etna here in Sicily is a good example of this, where the Mediterranean Sea crust is being forced under Europe. Another example is the range of Cascade volcanoes in the Pacific Northwest, such as Mount St. Helens shown here. Finally, subduction zones are characterized by large, deep earthquakes, such as the one that happened here in Peru. The two plates are grinding against each other where they meet at the base of the upper plate, so the pressures are very large. When one plate slips against another, a large section can move, causing powerful quakes.
Subduction is important for another reason. It provides the material that goes into making continents. We've already seen that ocean crust forms from mantle at mid-ocean ridges, but we haven't looked at how continents form. In fact, there are two ways that subduction can help make continents grow. The first happens when there are islands on the ocean crust that is being subducted. Instead of being carried down into the mantle, These islands are scraped off the top of the ocean crust by the continent. They wind up plastered onto the edge of the continent. We call this process accretion, and it's been important in several places, including the west coast of North America. Geologists studying California find that it is made of what started out as islands in the Pacific Ocean, some of them as large as Japan. These islands have been accreted to the edge of the North American plate. The other way to build a continent is through underplating. When the ocean crust subducts, part of the material melts and then re-solidifies on the edge of the continent. The process of melting and re-solidifying produces rock with a composition more like granite than basalt. So this is a way of producing the rock that dominates continents. Since continents grow through subduction, it means that continents grow at the edges, so the oldest parts of most continents are in the middle.
There is one form of convergent boundary that doesn't result in subduction. That happens when two continents collide. Continental rocks don't subduct into their mantle. Their density is too low for this. So if two continents come together, they have to build upwards instead. Continent-continent collisions produce large mountain ranges. The best example on Earth at the moment is the Himalayas in Asia. Between 10 and 20 million years ago, the Indian subcontinent crashed into the southern edge of Asia. Since then, it has continued to push north into the larger continent, forcing the Tibetan Plateau and the Himalayan mountains to form in the collision zone. The other obvious feature of this kind of collision is a large region with lots of earthquakes. In the case of the Himalayas, the wide band extending from Afghanistan and Pakistan all the way through central and southern China is subject to earthquakes resulting from this collision. However, since there's no subduction, there's very little volcanism in the area. The third type of plate boundary happens when crustal plates slide past each other. These transverse boundaries happen many places in the oceans, but there are only a few substantial ones on land. One of these is the San Andreas Fault system here in California. As you might expect, this sliding is often far from smooth. The friction between the two plates can cause smaller blocks to break off the main plates, creating a complex pattern of segments around the fault. There are several common features at transverse boundaries. First, there usually isn't much volcanism here, since most of the action is happening near the surface rather than down near the bottom of the plates. However, there can be many earthquakes, both small and large, like this one in California. Since the slippage that causes the earthquakes happens near the surface, there can be a surprising amount of damage done given the overall size of the quake. Another common feature of transverse boundaries is long, narrow valleys running very straight along the main fault. This happens because the ground here is weakened and hence easily erodes away. We also see offset features on either side of the fault, like this stream which approaches the fault and is then diverted northward before continuing on across. The San Andreas Fault is probably the most famous transverse fault in the world. It extends north from the Gulf of California up to Cape Mendocino, north of San Francisco. Different segments of the fault produce earthquakes of different sizes and frequencies. The section nearest to us last had a major earthquake in 1857. Since this section tends to produce large earthquakes on average every 150 years, many scientists expect that it could produce another one any time. Also notice the slight bend in the fault just north of Los Angeles. This bend means that a large part of Southern California is being forced northward against a hard section of rock in the Central Valley. This minor collision is causing the transverse ranges like the San Bernardino and San Gabriel Mountains to be forced upward. Many of the small to mid-sized earthquakes in the area are caused by slippage that helps push these mountains upward rather than any actual motion along the main fault itself. Eventually, it's likely that the section of rock causing the big bend in the San Andreas Fault will break, and the main line will go north through the Central Valley instead. but this could take millions of years.
So here are the key ideas connected to plate tectonics. First, the driving force comes from convective heat flow in the Earth's mantle. This flow forces more rigid plates at the surface to move around, making new crust in some places and subducting it back into the mantle elsewhere. The crust is divided into two different compositions: ocean crust made mainly of basaltic rocks and continental crust made of granitic rock. All of the action in plate tectonics happens along the plate boundaries. There are three major classes of these. First, we have divergent boundaries where plates split apart and new ocean crust forms. These are mainly found in the oceans, and they produce mid-ocean ridges. Where we see this on land, we get rift valleys, though over time, rift valleys will turn into new oceans. Convergent boundaries occur when two plates are moving together. If one or both plates are oceanic, then a subduction zone forms and one of the ocean plates is recycled back into the mantle. If they're both continental plates, then we get a continent-continent collision, producing a huge mountain range. Finally, transverse boundaries happen when two plates slide past each other.
Have a look at these two charts. The one on the top right shows a map of a plate boundary. Blue is water and green is land, with the deeper water showing a deeper blue color. The diamond shapes are active volcanoes, and the dark line cutting across the boundary is a region shown as a topographic profile on the lower left. This tells you how deep the ocean is or how high the land is along the dark line. So see if you can figure out what kind of plate boundary this is and what direction the two plates are moving. Make sure you explain your answers.
Here's another table to fill in so that you can list the properties of all the different types of plate boundaries. Notice that there are two categories each for divergent and convergent boundaries, since the features are different at each of them. For the last column, we've listed the possible features to add in. Note that the same feature might go in more than one row.